Hi everyone, can you all hear me?
Yeah.
Sorry, I am a bit late. I went to a, a wrong Zoom link and I
Oh
realized no
no.
one was there, so I had to switch to the CSD. Okay, I'm gonna admit everyone and then we will start. Okay, hi everyone, welcome to today's workshop on Introduction to Texas Data. Uh, Before we start, let me share with you the uh, tutorial material, which is also listed on the CSD workshop website. So this link is to the GitHub folder. Feel free to download it, to clone it on your computer. And then containing this folder is mainly the Jupyter notebook file, as well as a HTML file. The notebook file contains all the code, and then for you to run cell by cell sequentially, and then the HTML is rendered from this notebook file, and then it's for you to read and refer to the material afterwards without really go into details of the code. I'm also going to share with you let me see, a Google Colab file here. This is, if you click on this Colab, I've uploaded the tutorial in this space. It's more like a playground for you all to play with it, to run the code. Any change you made here will not be saved, so feel free to type anything and to experiment with the code as we proceed. And I'm also going to share this Colab file. If you have any questions during the process, or anything you don't understand, feel free to let me know anytime. Okay, so can everyone see my screen now? Okay, so this is an intro to text data. If you scroll down the table of contents, this is the main material that we'll be covering today. Mainly, I will be introducing three broad sections. The first is on selection and representation, basically how we represent text data numerically. And then the second broad section is about discovery, so how we perform knowledge discovery, research discovery using text data. And the third section is around measurement, which is, after we've performed the representation and discovery, how do we build measurements out of text data, right? And this tutorial will be introduced in Python. As many of you here, I personally started with R and earlier with Stata, but then if we're going to work with text data, Python and some Python packages, some machine learning packages is sort of unavoidable. So I've written this in Python, and then the goal here is not to introduce you line by line on what each line of code does. Instead, I will focus on what each step does. And then you can refer back to this material if you're interested in more specific coding details of specific Python functions. And I also want to mention that this tutorial is a really hands-on, a really practical workshop. So we are not going to explain in detail about the theories, the principle, biases, and ethical considerations behind each choices, but it doesn't mean that these are not important. In fact, thinking about biases and ethical issues is crucial when we are working with text data. So within each section, I've provided some basic principles for us to start with when we perform operations on text data. I will not go into the details, and I encourage you to look into the resources I mentioned in this tutorial and workshop to think more and to learn more about the principles and what to consider when we work with text data. So let's start here. We'll start by resources and materials. And here, this list listed out actually all of the libraries that we're going to use in this tutorial. For example, pandas and numpy are mostly used for data wrangling, numerical operations of data. Scikit-learn is a machine learning package, NLTK, Gensum, Spaces, mostly used for processing text, and it contains some good language models. And other libraries, including Request, JSON, Beautiful Soup, they're mainly used for scraping information from online, from web APIs. And if you scroll down to the table of contents, you will notice that I've included an appendix. First, on development of neural network-based models, and second is on retrieving text data using APIs. If we have time, I will go over this appendix today here. But if we don't, feel free to refer to these two sections on a little bit more information on how we use APIs to scrape text data, and also on more recent development of text data analysis, mostly BERT model and large language modeling. And in the winter quarter, I plan to offer another workshop focused specifically on using generative LLMs for social science analysis. And coming back to the resources, materials, this tutorial or this workshop is mostly based on this book, Text as Data, a New Framework for Machine Learning and the Social Sciences by Grimmer, Roberts, and Stewart. This book is especially useful in that it is designed for a social science audience, and it contains very useful introduction of a methodological toolkit of what we can do, and it contains a lot of existing research that's already published using the method mentioned. It doesn't contain step-by-step code demonstration, however, and that's what we're going to complement in this tutorial. Another book that I try to introduce you all here is called Practical NLP. It's a more technical book, which is focusing a little bit more from a NLP computer science perspective, but it's open source, and it contains a GitHub repository where you can go ahead and play with its code as you learn. So it's also a great resource. The Summer Institute in Computational Social Science Learning Materials is also another great resources. It contains the video on different sections of computational social science introduced, including how we obtain digital trace model, how we work on different parts of language modeling. So it's also very good resources for you to check out. Actually, one of our alumni, Connor Gilroy, also taught one of the sections in this Summer Institute of CSS. So I really encourage you to check out. Additional resources can be found in the reference section of this tutorial. Okay, so now let's go to the selection and representation section. And also, as I mentioned, feel free to interrupt me anytime or post question in the chat if you're confused about anything. So what is selection and representation? When we work with text data, the first step is always to consider how can machine or how can the models understand the data we present to it, right? Because when we present the text, whether in English or in other languages, the machines don't understand it unless we convert our text data into a numerical format. This format, this input format can only be understood by the computer itself, right? So in this section, we will mainly be learning about how we select and represent text using different kinds of methods. But before we start, there are some key principles to keep in mind of. Principle one is that when we are constructing corpus, it's really important that this corpus needs to be useful. It depends on the research question we have and also the population that we're interested in studying. Principle two is that there's no value-free corpus construction. We need to be really mindful of the population we represent and also of their ethical ramifications when we select a corpus. And principle three is that there is no right way to represent a text for all research questions. And there's the principle four is that the best assurance that text representation is working is extensive validation. How to select and represent text using Python? We will mainly walk through an example using the NLTK and the scikit-learn and matplotlib package. Matplotlib is a little bit like ggplot in R, which is mostly used for plotting. We'll be mainly using all three packages, possibly also the word cloud package to pre-process text data and represent it numerically. If you go to the cell below, feel free to run it by clicking on the triangle here on your Google Colab, or with Mac users, you can click on press Shift and return. So this cell will run automatically. So here we're importing the necessary libraries and downloading the data files. Note that we only have to download these data and package file downloaded once, and then next time when we run it, we'll just have to import it from our environment. So here I'm going to run it again so that we know where this is all coming from. You can notice that Google Colab is executing the cell. And then with this right tick mark showing that this process is completed. And now notice that we've downloaded everything. I'm actually importing the additional libraries to tokenize the words, which is basically to break the words into pieces of words and to break our corpus into pieces of words and phrases. Stop words, a data set contained by the NLTK, which contains frequent words that commonly appear in a bunch of texts, but are not pretty much useful to our own task. Word net lemmatizer is a lemmatizer which helps us to reduce the word to its root form. I'm also going to import the movie reviews data set, which we use as an example in our tutorial today. So if we want to examine the movie review corpus, note that this is a Python object, right? So the fields after the dot is actually means the method that's associated with this object, because Python is mainly an object-oriented programming language. So if we want to examine, what this movie reviews dataset contains, for example, we can use this file IDs method. We can actually notice, it looks like it contains subfolders. This is one is calling negative, and then under the folder, there's different text files containing different pieces of movie reviews. So this is what we guess, but we can also check out what are the categories inside this movie review. Inside this movie review objects. We notice that there are actually two subfolders. One is called negative, one is called positive. So listed here are all different methods, and we can also check out what are the most frequent words appearing in this movie review data set. So we can really notice that the most frequent words is this comma, which appeared over 77K times. And then all the and then the period, which are all very common words, but we're thinking, are they really useful to our research purpose? Probably not, right? So one of the key steps before we really turn our text data into numbers is to really clean the text, pre-process the text data. And then we can then make the movie review data into really a data frame, so that for us to easily view it and also for us to process it using pandas. And this data frame is what we come up with. It contains two columns. If we run it here, you can notice that one column is called the label, which is the categories that we just check out, contains positive and negative label of a movie review. And then each row is a review data a user given to a certain movie. And this review column contains the actual content or actual text of the review. As we just said, this text data is really unstructured, it's really noisy. So we need to clean it, pre-process it before we really convert all the text data into numerical representation. We need to consider what is the unit of analysis of our text data. A common way is really to treat each document as a unit of analysis, as what we have here. It's also possible, of course, to use each word or each phrase as a unit analysis, which if you have a large corpus will generate with a really long data set with a lot of with a large number of observations, of course. People might also consider dumping the entire corpus as their unit analysis. This all depends on what we want to present and how do we want to approach our research questions. So here, each unit of analysis is one piece of text document, and then it has a label given by this NLTK dataset is either negative or positive. So how we're going to reprocess this text data, we're going to reduce the complexity of it by lowercasing all the words, by removing the punctuation, by removing the stop words, and then by reducing the words to its root format. And also, sometimes people also filter by frequency because they don't want words to appear in, for example, over 90% of the documents. So that for further processing. Here, I'm defining this pre-processing function, which contains the steps that we mentioned above. For example, this step contains using Python list comprehension, we're telling Python we're only selecting text, which is tokens, right? We're breaking the text into tokens, and then we're only keeping it if it is alphabetic, and we're only keeping that if the word is not in the list of the stop words. So after we define this function, we need to apply this function to our data set of movie reviews. And we generate a new column from this review column after we apply this process text function on this review column. So what do we have afterwards? This df head is just helping us to take a preview of what's contained in this data set, right? In this data frame. So we can actually notice that this process review looks cleaner, definitely, than the raw text. It doesn't contain any punctuation, and some very common words like is, it is disappeared, right? But are we confident that we've cleaned all the nuances that we don't want? Sometimes we don't know until we actually work on the analysis. So it's keep in mind that this pre-processing might be an iterative process as we proceed with text data. Here, I'm also doing a dedupe process based on the process review. This should be a pretty clean data set, but in the real world setting, we often face with a lot of noisy data that they might contain some duplicates. After we clean the data, after we're having a baseline confidence of, our data is cleaned, we'll try to convert our data or our corpus into variables or into features, right? Note that what we are trying to compose is a document feature matrix, and each feature you can understand that as a variable, so that in this matrix, each row will be one of our document, which is our unit analysis, and each column represents a feature, a token, or a term. And this term can be a word, it can be a phrase composed of 2 words, 3 words, depending on how we define it. But the goal is to represent our corpus into this as this DFM or document term matrix, and then prepare it for the next step processing. We start from the most basic feature representation so that we have this row and we have this column in our matrix, and each cell, the value of cells represent the frequency of words. So let's see how we do it. We first import the count vectorizer and TF-IDF vectorizer from the scikit-learn module. And then we're trying to initialize the vectorizer and then create an instance of a count vectorizer, which, just as I said, we're creating a bag of words matrix by having each column represents a term. So these are the feature names. These are like the names of possible features or variables we're looking at, and each row represents a document. And this is, I've converted this sparse matrix into a dense array for us to take a look at this matrix more clearly, you will notice that most of the values are 0. For example, we might want to see, oh, this document 1 does not contain this feature of AA. It doesn't contain this term. So the value here is 0, etc. To see it more clearly,
can I ask a question real quick?
The bag of words representation as a data frame to take a look at it. So you can notice that, oh, these are the features that is contained in all of the matrix. This is like the first 10 features, our first 10 variables. And I'm also showing the first 5 rows in this data frame. We can also take a look at what are all the features, for example, in this document 0. So if we want to consider document 0, which is the first row of this data frame, we want to learn what are all the possible variables, or what are the possible tokens contained by this document of movie reviews. So it contains film, contains movie. So this number here, value here, represents the frequency or number of times each word appears in this document. And here we might also consider, oh, this film, movie is not really adding additional information to my research purpose. It's kind of expected that a movie review will contain keywords such as film and movie. So we might want to go back and change the stop word list as we observe all these features and remove those that are really frequent but are not adding additional information to our research task. You can also play around with this data frame a bit to see what are the most frequent words across all the data frame. So this is what this data frame tells us. These are the most frequent, 20 most frequent words based on the times that they've appeared in this corpus. So building off from this bag of words representation, there are actually 2 fundamental approaches we could consider. One broad area is probabilistic. So in probabilistic models, we make assumptions about the data generation process using probability rate. The other approach is called algorithmic approaches. If we consider this 2 approaches in a linear regression, for example, it's like if we're describing linear regression from a probabilistic perspective, it's like a normal linear model. But if we're thinking of it from an algorithmic perspective, then it's a least square approximation. So my understanding is that both approaches are using different languages to describe the same thing. But when we're working with text data, we can also think of method as in these 2 broad approaches. Building on the bag of words approach, there's this TF-IDF approach where we assign each words, instead of using the frequency that appears in this document, we assign the weights or the cell values of this matrix based on their importance, a certain measurement of importance. And this measure will be really important if we dive deeper into the algorithmic approach, where each term can not only be represented by one number, it can also be represented by a vector. And then the meaning of words and the relationship between tokens can be understood by their measurements of similarity using the vector space that they are built in. So this is where this fundamental concept is built in as we proceed. But here we're actually going to look at the pretty canonic representation of TF-IDF of representing text. TF-IDF stands for term frequency inverse document frequency. If you look at the formula here, this measurement contains 2 parts. It's a product of TF, which is the term frequency, and the inverse document frequency. So basically, it's measuring how important a word is, not only to this piece of document, but also to the entire corpus. By first calculating how many times a term appears in a document, but also calculating how many documents in the entire corpus containing this term, and have it divided and have the total number of documents in this corpus divide this number of documents that containing this keyword term. So what is TF-IDF means is that it's actually picking out those words that are frequently appearing in specific documents of our corpus, but is penalizing those words that appear in a lot of the documents across the corpus. So it not only want this word to be frequent, it also want this term or this phrase to be really unique across the corpus. So this weight is different from the frequency value that we just talked about. It's like building a step above the bag of words approach and assigning a more granular measurement of how important a term is within an entire corpus by using the TF-IDF method. But the actual implementation of TF-IDF is really also pretty straightforward using the scikit-learn package as we just imported. And it's actually the same, but we're just using the TF-IDF vectorizer instead of the count vectorizer. And here I'm also having it display the feature names and then convert this sparse matrix into an array for us to see it more clearly. And these are the functions for us to show what are the top words by their mean TF-IDF score. So the higher score means that a word is more important in this corpus. So if we only look at these top words, I personally feel that it's not too much different from the count vectorizer's result, right? So it looks pretty much the same from the step that we did above. So if we're really interested in what are some words that TF-IDF thinks is important, but sort of ranks low in terms of words frequency. So this is all part of the exploration process. So we can calculate the rank difference by picking out words that rank relatively higher in the TF-IDF ranking, but rank a lot more lower in the frequency ranking. And I ranked this difference by the rank difference so that we can actually see that, oh, probably this UR word ranks relatively higher in TF-IDF and a lot more lower in the frequency rank. And we can actually see that some of the words are hard to understand because, for example, this UR is definitely coming from UR, but we've reduced the word to its space format, and also we've removed all the punctuation, so they can be a little bit different from their raw format. But we do see that by browsing through all these words, it feels that, for example, this nostalgic, engrossed, crawling, it contains some words that are pretty unique to movie reviewers. They're expressing some feelings or using some adjectives to describe the movie that they are giving review of. But definitely these words are not coming up really frequent in the frequency count. So that this is a way for us to really know, oh, these are some important words given by TF-IDF, but they're not necessarily ranked very high in terms of word frequency. When we are introducing to our audience of our research article, for example, we want to show them, oh, what are the important terms that appearing in our corpus? We might choose TF-IDF over the frequency rank because TF-IDF is giving us a more granular measurement of importance of terms in our given corpus. We can also try visualize the data by using the word cloud. So in this step, I'm actually using the word cloud function from the word cloud package to plot, to give us a word cloud plot based on the TF-IDF weights. And the larger the font size of the word means that the higher the score this word has. And again, we can actually notice that it's kind of expected that movie and film ranks really high in terms of TF-IDF. And if we want our text to be cleaner and we want to surface other important words, we might go ahead and go back and remove this movie and remove this film. I might even remove one, for example, because they're not adding anything to our understanding of our research task. It's kind of expected that movie and film will appear really frequently. And you might also wonder how many words are included in this word cloud. So I had this question as well when I was playing around with this word cloud package. It feels that so first, the color doesn't really mean much of a thing, right? It's just an aesthetic thing in this package. But then the words, the number of words contained is really determined by the size of the word cloud figure, and it's also determined, I guess, by the size of the font that you can input as a parameter. So if you want more words to be included in this word cloud picture, you can adjust the size of your picture and also adjust the size of the word, so that the font size of the word, so that more or less words will be presented. And this is also a good technique to be used when we're in this initial exploration phase of our data. We might also delete this could, for example, or this quite, because they're not adding additional information to our understanding of the corpus. So that was all about beginning steps of how we represent text. As I have mentioned, there are definitely more advanced ways to represent text, right? Instead of representing each word or each term as a number, we might choose to represent each term as a low-dimensional vector. And we might also perform part of speech tagging based on the nature of the word or based on its functionalities. But the logic and the idea sort of starts from the back of words and from the TF-IDF representation. If you're interested in learning more about more advanced methods of how we represent text using word embeddings or using POS, feel free to reach out to me via CSDE consultancy or just send me an email, for example. Do we have any questions before I proceed to the next section? Yes, Jess. I see your hand.
Oh, sorry. I thought I lowered it a while ago. I will ask you later.
Oh, okay. I realized seems that my earphone is not connected to the to my laptop, but I hope you're all hearing me okay. I'm using my Mac speaker right now. So the next section is actually about discovery using text data. This comes down to a research approach that we might consider when we work with text data. So when we analyze text data, it's kind of different from the standard deductive approach that many of us are trained on, that we will start with a theory model, we will build our hypothesis, and we'll go ahead, collect data to test our hypothesis, and we'll present some results. Especially when working with text data, it's sort of recommended that we take this iterative approach, right? We definitely have our theory and model in our mind, but then we go ahead and collect our data. But a lot of the learning and discoveries happen while we're doing the data analysis. And then we may then proceed to build up our hypothesis. So this iterative model when working with tests is really important because following a combination of deductive and inductive approach will help us really see what's important there in our data. And then it will even help us form or rectify our research question as we go along. So this discovery part is really important when working with text and working with other types of data, as I would argue as well. At the early stage of the research process, as I said, the discovery will help us refine our research questions. And then discovery often involves using both supervised and unsupervised learning techniques, actually. And you may question, what is the difference between supervised and unsupervised methods? I think to put it in a nutshell, supervised method means that we have a y variable to start off, right? So that we'll be able to use this outcome variable together with a bunch of predictors to train a model. But unsupervised methods is more like we don't have this outcome variable to start with. We're just exploring our text by using this unsupervised method, but we're not using the model to predict a given outcome. So what are the principles we need to keep in mind of when we're discovering text? First of all, is that the text data models complement our theory and substantive knowledge. We cannot, for example, start with a corpus we have and see, oh, what can I discover from my corpus without any knowledge of theory or without any research question in mind. In that way, it's often, I myself, for example, will often find it really hard to interpret what that initial result shows. So contextual knowledge will amplify our ability to make computational discoveries. And the second principle is that there's no ground truth conceptualization of our text data. Only after a context is fixed can we talk meaningfully about it being right or wrong. And the third principle is really to judge the concept, not the method. Only the utility of a concept matters when you assess the concept's value. And the principle 4 is that it's ideal if we could separate the data. After data is used for discovery, it should be discarded, right? Ideally, if although we know that our text data, our corpus is really valuable, so we don't really want to discard it, especially if our data set is not that large. But ideally, after our data is used for discovery, it could be discarded in favor of new data for confirming and testing our discovery. This is especially true in a supervised setup. There are broadly speaking, 4 classes of methods we could use to perform knowledge discovery using text data. The first broad section is about discriminating words. So we try to identify words that are used disproportionately by a given group of documents. For example, we might want to see what are the different words that are disproportionately given by two political parties, and then perform analysis over the meaning behind. And clustering means that we are producing a partition of the text so that for each document, for each unit of analysis of our data set, we try to assign it to a cluster or to a group. And then we observe this pattern of different clusters or different groups of our text data, and then we should be able to come up with some generalization about what different groups of text are talking about. And a third type of methods is called topic models. Topic models is a little bit similar to clustering in that it tries to group our documents, right? Try to discover some latent patterns of our documents. But it is also different in that while clustering try to assign each piece of our document into a group, into a specific cluster, topic modeling is actually try to discover a set of K categories where each document holds a proportional membership in all of the topics. For example, we might find the output of a topic model that topic 1 has this probability of 0.1 belonging to a certain topic, and the probability of 0.2 belonging to a second topic. And this topic probability adds up to 1 for each document. So you will be able to see, oh, what are the top topic of each document? And you can also be able to see what are the top documents under each document, under each topic this model comes up with. And the fourth general broad category of methods we could use to discover text is called low-dimensional document embeddings. This is just the method related to word embedding that I just talked about. So the idea is that we project each piece of our document, for example, each sentence or each term as we choose, into a vector. For example, this vector can have many dimensions. It can have 300 dimensions, as long as this number of dimensions is lower than your number of observations in the corpus. And then the beauty of representing each sentence or each document as a vector is that we can use the mathematical calculations to calculate the relationship between our documents, right? So a really famous example is that king minus woman equals queen. So behind this simple example is that each term or each document is projected into a vector, and then this embedding will help us understand what is the meaning or what is the relationship between the documents or terms that we try to discover in our corpus. So word embedding can also be used as a really useful discovery technique that when we try to understand more about our data set. In this tutorial, in terms of how we implement some of these methods using Python, we will focus on the method of topic modeling and some extension of this method for details. If you're interested in other 3 classes method, feel free to reach out to me and refer to the resources, to the book and the tutorials linked to this document. So topic modeling, probabilistic topic models suppose that each document in the corpus is a mixture of a fixed number of underlying topics, and each topic is a mixture of words, right? So the goal of topic modeling is to identify the topics and their associated probabilities for each document, as well as the words and their associated probabilities for each topic, in order to maximize the likelihood that we actually see the data that we observe. So we will go into details to look at this canonical form of latent Dirichlet allocation for topic modeling. This is the most, I would say, the most classical model that most people working with text will understand or will try to understand as their first step of understanding text as data. There are many extensions built on LDA, and of course, there are more recent advancements of using, for example, neural network-based models to come up with topic modeling. But LDA is really good to know about, and it's really a good model to start with if you're ever thinking about building topic models. LDA is a Bayesian hierarchical model, right? So it assumes a particular data generation process for how an author produces a text. We first suppose that when writing a text, the author draws a mixture of topics, which is essentially a set of ways that would describe how prevalent particular topics are. And given that set of ways, the author generates the actual text. For each word, the author first draws the word's topic, and then conditional on the topic, the actual word is drawn from the topic's specific distribution. And this topic-specific distribution is common across the documents and characterizes the rates at which words appear when we discuss a particular topic. This is the mathematical representation of the process we just described. As I said, so the goal is to really maximize the likelihood of us seeing the data we observe given the parameters that we just talked about. You can notice that the distribution of topics in document D and the distribution of words in topic both follow a Dirichlet distribution. The inference is really always conducted using method like variational inference or Gibbs sampling, and is readily implemented by both Python and R packages. So how to perform LDA analysis using Python? we will still build off, sorry. When I click on the cell, it sort of drifted away. We'll still be building off from our movie reviews data set to see how we can build an LTA topic modeling using this data set, right? Review, this is the data frame that we're working with, and then we are mostly going to be using this processed review column because this column is cleaner. And first is the same as we just learned in the first section. We need to vectorize the text data. We need to turn them into a document term matrix. Because we are not interested in single documents, we're interested in discovering the global patterns of our data set, right? But an additional update, which is a little bit different from our first section, is that instead of converting each, separating our text data into pieces of words, what we're trying to do here is separating or tokenizing our corpus into n-grams. So what does n-gram mean? N-grams are continuous spaces or sequences of words or tokens. A unigram is essentially a single word, right? But a token or a n-gram can also include a bigram, which is usually a sequence of 2 words, and the trigram is a sequence of 3 words, for example. So we can break our text not only into words, but also into phrases. And this is all can be customized when we perform this vectorizing step. So here, I'm using still the TF-IDF vectorizer to construct this document term matrix, but instead of building it only using unigram, I'm giving it a range of, I want my words or I want my phrases to range from term 1, from 1 to 5, so that I might have a maximum of 5 words composing a term. And then I also want to set a cap of ignore terms that appear in more than 95% of the documents, and then also ignore terms that appear in less than 2 documents, right? So this is all ways that we could control how we want to confine our vectorizer. And then here we fit and transform the processed review column. We can check out the shape of the resulting document term matrix. And notice that this 1998 means that we have this many pieces of documents in our data set after we clean it, after we dedupe it. And this over 4,000 column means that we're coming up with this many number of features or terms when we have TF-IDF going through an n-gram of range 1 to 5, and then of given all these different parameters. And then we can apply the topic modeling LDA by running this LDA function, which is also imported by the scikit-learn package. LDA is also pretty readily implemented by R. So if you're an R user, feel free to check out the LDA package. So here I set the number of topics as 5, just as an initial starting point, right? And also I set up a random state. It's like a setting seed so that the modeling process is reproducible every time we run it. And then we want to examine the topics by first check out what are the top n-grams for each topic. So this is a function to display the top n-grams for each topic. So here are 5 topics, right? And then for topic 1 is more know, react. Topic 2, movie, film. So this is probably another time that we really want to go ahead and remove all these frequent words because they're not adding anything to our understanding of the data. And topic 4 seems that it belongs to a type of topic that people are saying this movie is pretty fun, is pretty interesting, around some chicken run, for example. Topic 5 is all these words, which don't seem to be really intuitive when we look at it by the first sight. So the next step is really to look at the actual documents that have a high probability of belonging to each topic. So when we try to interpret the results of topic modeling or interpret the results of any of our discoveries, you can think of the method as relying on a spectrum, right? So on the one side of the spectrum is that we only rely on the model results. We only look at what are the probabilities of each document belonging to each topic. And on the other side of the spectrum is that, we don't rely on any model. We solely look into the text itself. We only qualitatively read into the text. And actually, a good approach is always a combination of both. So it sort of stands in the middle of the spectrum so that we rely on some of the model statistics, but we also rely on qualitative reading of the text to understand, to interpret the model output. So here I'm setting a threshold for topic distribution. I want this code to return to me 2 top documents that belong to each topic with a threshold of a probability of higher than 0.1, for example. So what do we get from here? We can actually notice that, to my surprise, or at least originally, I noticed that we still have duplicated, like these 2 rows look more or less the same. And no wonder they are affecting these topic models, right? Because they're mostly the same, so that they're affecting how the model recognize the distribution of words. But didn't we already like deduped our corpus before we conduct topic modeling? So this is another time we might want to go back to take a look at our raw text even to compare, are they exactly the same, or is there something wrong with my pre-processing? Before we can really dive into, we need to run the model again after we clean up all these duplicates, and then run the model again, and then properly interpret that. And similarly, for topic 4, you can actually see that this 2 document 1113 and document 1272, more or less represent same text, right? But so the good approach is really to see, whether this result makes sense to me, and then I'm going to dive deeper into the text to see what's going on there. So here we want to examine topic 1174 and topic 1759 in this data frame, which they're both appearing under topic 1, and it's really, giving us a weird model results. So we want to see what is the raw text here. So the TLDR version of this discovery is that they're not exactly the same, and they might differ by some specific punctuations, by some specific noise, even when we dedupe it based on the processed text column. These 2 columns, these 2 rows of processed text are not exactly the same, but they're actually representing the same review. So this is a time that we might want to go ahead and go back to our text data again to really clean them up, and then to make our text meaningful. And then before we actually go back to the topic model and then try to interpret what the result is. And notice that when I set up the LDA, I set the initial number of topics as 5. But this is not a given parameter. We actually need to choose the optimal number of topics based on certain type of measurements. Is a hyperparameter that we need to decide. For LDA, there are following methods that we can rely on to choose the optimal number of topics. There are perplexity scores, there are coherence scores, we can rely on manual interpretation, and there are grid search, cross-validation, for example. And perplexity scores can be implemented using Python's GenSum library coherence model, for example. And LDA package in R also offers a few functionalities for us to check out the different metrics associated with each number of topics that we put in, right? I want to stress that the importance of really manually look into the topics and interpret the topics. For example, after we come up with all the topics from topic modeling, we might notice that, oh, these two topics, although they seem to contain different terms, contain different words, but they're actually telling more or less similar meanings, especially if you're not working in English, right? Some languages, like the Chinese tech I work with, sometimes they use very different words to describe basically the same thing. So we might want to collapse the number of topics and give it another try. And similarly, if you're finding that one of your topics is containing a mixture of possible terms that can be possibly broken down into different topics, you might want to increase the number of topics a little bit to see whether they make more sense according to your own understanding of what each topic represents. So the key is that relying on the statistics, the scores is definitely a good approach, and also something we need to present when we are writing the model, right? How we build up the model, how we chose the model, how we chose the number of topics. But also manual interpretation is also crucial when we are doing topic modeling, when we're doing discoveries through text. So this is something really important to keep in mind of. So that was about LDA, and then thinking about what is incorporated into this LDAs, what is the output of this LDA modeling? We can actually think of one of the output as the theta matrix, as the distribution of topics across our documents. So the theta matrix of the LDA output is actually, you still have your documents as your data frame, right? You have each row of your corpus as one unit analysis, your document, but this output of LDA of any topic modeling is that it will give you a matrix where each column represents the probability of a document belonging to a topic, a certain topic. For example, in the LDA model we just built off, I will have 5 columns representing topics 1 to 5, and each document will have a probability of belonging to those 5 topics. I might have document 1 belonging to topic 1 with a probability of 0.1, and belonging to topic 5 with a probability of 0.3, for example. And with this matrix, it's actually very easy or possible for us to incorporate some structure into LDA. So you may think of, oh, I have this matrix, right? Where each cell value represents the probability of my document A, B, C, D belonging to a certain topic. Can I model it against some of my covariates? So for example, am I interested in learning about, is there a difference between different genders, between people of different racial, ethnical backgrounds in speaking of, in having different topic in speaking of text that of different topics, right? Is woman more prone to be talking about topic 1 than topic 3 than males, for example? So with this theta matrix, or the topic distribution matrix, we can easily model our topic prevalence or topic probabilities, or the exact words used inside each topic, which is given by another output matrix of the LDA model against our covariates. So this is called structural topic models. Is mostly implemented in R. The assumptions is a little bit different from LDA, but they don't differ much. Here we call it, we incorporate this structure with upstream covariates, right? Covariates, right? So that your covariates is in the upstream predicting your topic probability. We might also consider some structure with downstream covariates. For example, you have this matrix of topic probabilities, but we are interested in learning about, can these topics be used to not only maximize the data generation process, but can they be used to predict an outcome variable that I have? Note that we cannot manually use the results of LDA to directly predict an outcome variable in our data set. They don't work well. Instead, there is this method called supervised latent directly allocation, the SLDA, which when it's trying to come up with a model, it's not only maximize likelihood of what we see the observed data, but it also try to predict an outcome variable that we specify. Both these patched methods, the upstream and the downstream methods of incorporating the covariates, are implemented by R. So in reality, when we work with probabilistic topic models, I would say R is the to-go choice in terms of language. I'm not aware that Python has anything on STM or SLDA, for example. So this is something to also keep in mind of. So do we have any questions before I proceed to the last chapter of building measurements out of text data? I'm gonna pull up the chat here. Okay, so measurement. So when we think about what we've done just now, right? We've represented our text numerically as the first step. We've cleaned up the text. We've done some discoveries using our text data. Right now we have a good knowledge of what our text data contains. And we have refined our research question. The next step is usually we want to build some measurements out of text data. You may notice that with our text data, be it from newspaper, from news, from web resources, from social media, a key characteristic of our text data is that they usually come in really large volume. They come with a lot of variation in the text, but you don't have a lot of covariates. You don't have a lot of measurements or variables to work with, as compared to, for example, if you have a survey data set, we usually have a lot of variables to start with, right? So when we work with text, a key step is always we have to build some type of measurements before we can use text data to a next step, modeling, inference, for example. So measurements, as I've put it here, involves quantifying specific attributes or behaviors within text data, right? This really lies in the beauty of text data, is that we can create some really customized measurements for a wide range of phenomena that are often difficult to quantify based on other data types. I've read through, for example, some researchers are measuring political bias built in a certain document. And in my research, for example, I've built in measurements measuring if people are liberal or non-liberal towards premarital sex in a patriarchal context. So this measurement building is really dependent on your research goal, and it can be really flexible. If some of us are qualitative researchers, you may notice that this is a step that is really common in qualitative approach, right? We want to code our text data by creating some custom measurements, and we're coding the text data. We're reading into each documents ourselves, right, by several human coders. This process can return pretty high quality measurements, especially, if we have multiple coders who are properly trained to code our text, but it can also be time and resource consuming. So what I would suggest is that we would follow a supervised approach, right? We can first start by coding qualitatively. We create some ground truths that can be used to validate a more automated approach. So it's good to start with some qualitative coding to obtain this amount of high quality labels of our data set before we really dive into using different types of machine learning approaches to build this measurement. So here, I also include a varieties of approaches that we could use to build up measurements. The most straightforward way is like we've just learned about word counting, right? We can come up with a variable counting some specific words that appears in our document that is of our research interest. Or we can build a measurement, for example, based on an existing dictionary. That is, for example, how we conduct sentiment analysis. We want to measure the direction and the intensity of emotions built in each document by conducting a sentiment analysis. Often we will rely on a pre-built dictionary, where in this dictionary or in this package, it contains a large corpus of terms and as keys, and the values are just a number of the sentiment they represent. And when we are conducting sentiment analysis, we're essentially aggregating our document, the words in our documents, and by aggregating the values associated with each term, so that we come up with the sentiment measurement of entire document that we're looking at. So this is more of a dictionary-based method. There's supervised classification methods, which I will go ahead and introduce a bit deeper in this tutorial. I also want to mention that the generative LLM can be such a great tool that we use to build up measurements, in that it sort of commands the ability to understand and generate new text, right, based on our text input. So this is also something to be considered of, especially if you don't have a good amount of labeled data to start with, right? So you don't have an existing measurement, existing values in your proposed measurement to start with. You might want to try out some unsupervised method using LLM. So here I'm gonna introduce the how-to using Python part by walking you through an example of how to train a supervised classifier, right, using Python. So as we've talked about, what does supervised mean? Supervised means that you have an outcome variable to start with, right? You have you want to train some model, and then you have your predictor and you have your outcome variable available. This is what we mean by supervised. Classifier, what is a classifier? Which is pretty straightforward to its meaning of English. So we try to classify our unit of analysis, our observations into different categories. It can be a 1, 0 category if your measurement is like binary. It can be a multinomial, right? Depending on how you want to build your measurement into. But this is the essential meaning of supervised classifier. And then how do we do it using Python? You will notice that I'm still extensively using the scikit-learn package. I'm importing some important functionalities of scikit-learn called train test split. I am introducing logistic regression to start off as the most straightforward and parsimonious model that we can take a look at. I'm also importing some metrics to measure the performance of our model. And all these additional packages, functionalities have been imported in the above steps. So I'm not doing it again here. I'm still using the movie reviews dataset that we are working on throughout this tutorial. But for illustration purpose, right, I'm gonna insert some artificial missingness in the label. Remember, we have a label of positive or negative. I'm converting here of positive into 1 and negative into 0. And I'm replacing some of the data I have into missing data. Suppose you really have a measurement, you have a good measurement that you want to use for your modeling, but a lot of this measurement is missing, or you only have the time to code a certain amount of your data set, and then the rest of the data set is missing, that you really want to impute this missingness in your measurement by making so that you can make it useful for your next step modeling. So this is what we try to do. By inserting some missingness in our data set, you will notice that I still have a number of documents, the similar 1,998 documents, but I have this 400 something of number of documents with this missing label. So we don't know if they're positive or negative, right? So here I'm actually, before we build models, in any context of supervised modeling, we need to split our data set into a training and into a testing data set. What is the thinking behind this is that we need to train our model, train our logistic regression model in this case, using the training data set, right? And then we need to separate out a data set that this model hasn't seen before for us to test out how well this model performs. Because our goal here with machine learning task, with this classification task, is not really to understand what each parameter represents, right? We're only interested in, oh, if my classifier works well, if it is good enough, persuasively, we're confident enough to use this model on our data with the missing measurements. So we really need to know how well our model performs on data it hasn't seen before. So this is the idea behind this train test split. So I'm first picking out the part of the data frame where it does not contain the missingness, right? I need to split both train and test out my model based on the existing measure, the available measure I have. So right now I'm setting aside this missingness, this missing part of my data set. And then I need to do this train test split. Notice that I've set the test size to be 0.2, and still I set a random state here to make the process reproducible. There's often also another set to be considered of, is called validation set. So it's sometimes recommended that we separate our label data set into not only 2 sets, training and testing, but actually into 3 sets, into training, validating, and testing sets. So what does this validation set do is that the validation set is used to fine-tune some hyperparameters of the model that we built. And then after we fine-tune it, examine how it performs on our training, on our validation data set, we use the test set to do the final evaluation of the performance of the model. In this example, however, we did not include this validation set, both for the simplicity of how we illustrate the process, and also because our data set is inherently pretty small, and I've included a lot of variables here. So, but I will mention how we use it as we proceed. As we notice, so what is the size of my training and of my testing data set? I have a little bit over 1K of training set, and I have around 300 observations to test out my model. And I also have this 427 observations, which, is missing. I don't have that labels. Similarly, I'm building feature extraction the same as TF-IDF vectorizer. to build this document term matrix. And here I have selected the number of features to be 1,000, so that max feature of 1,000, so that essentially I'm only restricting the number of predictors into 1,000 to predict my label, that is my outcome variable of this category of review. If we look at this shape of our data set, we actually notice that we probably have included too many variables, right, in this process, so that we run into the risk of overfitting. So what does overfitting means is that you have a lot of predictors to start with, right, to build your model, but your data set is not large enough. You don't have a lot of observations. So what will come out of this possibility of overfitting is that your model will perform really well on your training data set, but it does not perform well on the outcome or on the data set it hasn't seen before. So it will probably perform really badly on validation set and on testing set. So this is something to be kept in mind of when we came up with so many predictors that we want to use to train our model. So what are the predictors? These are some sample n-gram features: ability, able, absolutely. So we're actually interested in learning, is this term absolutely, all these terms giving us a predicted probability of a certain document belonging to a positive review or belonging to a negative review. So this is essentially what we're trying to do here using this document term matrix by building a logistic regression. So here we use the document term matrix we come up with to train this logistic regression. And then we evaluate here both on the test set, and it's also possible to evaluate on the validation set. So a question I had when I was learning all these processes is that how do we know if we're overfitting, right? How do we know if your model really has a small bias, but it has a large variance so that it's, it doesn't perform really well on data it hasn't seen before? So this process is really done by iteratively doing it. If you have a test set, if you have a validation set, for example, we might change the number of features we put in. We might reduce it to 500, or we might increase it to 1,100, for example. And we test out how our model performs on data it hasn't seen before. Example is that, for example, if we increase our number of predictors, and then we train this model and we test on the validation dataset, if we notice that the performance of our model continuously improves on our training dataset, but decreases on our validation set as the number of features increase, right? For example, if I choose 1,100 features in this model, I noticed that, it performs better, but then the on the training set, but the prediction power or the performance on the validation set drops as the number of features I put increases. That might be a sign of overfitting. So the performance metrics are telling us, the model with so many features, variables, predictors is not performing really well. The model is being too complex that we don't have enough observations, right? Here, but how do we evaluate the model, right? I'm presenting to you some measurements, pretty reliable metrics that we could use to evaluate how a model performs. With Python, with scikit-learn, logistic regression, and all the machine learning models, it has this classification report automatically calculated and presented to us. But essentially, the essential idea is that you will have a confusion matrix where you will have a tablet of true, false, and true positive, false positive, true negative, and false negative, right? And for each category, the model predicts, right? It classifies into. So by default, when we predict when we have a predicted probability of a document belonging to a certain category, we have this predicted probability of 0.5 and above categorized as 1, and this predicted probability of below 0.5 categorized as 0. And of course, this threshold could be adjusted as well. For each classified or each category the model classified the document into, we are evaluating how good the prediction is using the test data set here. So this is the test data set I came up with during the train test split process. And here are some metrics we can look into. The support just means the number of observations used. The precision you can understand is it as for the positive category, for example, of all the positive cases this model identified, how many of them are actual positive, right? So some of them are actually negative, because we already have the label in the test set. And then recall is another metrics. It actually measures of all the positive cases in our data set, how much does our model capture? So these two metrics give us a pretty good measurement of how well our model performs. So you may notice that on the negative category, the model performs a little better on precision and less well on recall. And then for the positive category, it performs better on recall and performs worse on precision. And F1 score is more of a average and macro aggregate of these two precision and recall measurements. And then this metric, performance is, I would say, is good enough, right? The model can be used, but it can definitely be improved based on the method. So there are a lot to consider when we're training and when we're evaluating data set. So this can only be a basic step to start with, and then your model could be fine-tuned, right? You could reduce your number of features in the setup and see how that model performs. You can even perform a variable selection by using some, regularization techniques such as lasso or ridge. You can, so there are a bunch of different variable feature selection methods in the linear regression setup. Feel free to read into them if you're interested in learning about how we improve the performance of the model. So here, the beauty with logistic regression is that you can actually see the parameters, right? So we can actually see that what are the top 10 positive features that predict this label of 1, and what are some top 10 features that predict this feature of 0. And you can also present this in your research result to see, to prove that your model makes sense. And after we're confident that our model is doing pretty well, we can use it to impute the missiness in our measurement. Recall that I have this 400 something of observations that I don't have this measurement, right? I need to impute the missingness. So then we just use this train model to predict based on our unlabeled data set. And then we can also analyze some results. In our case, since we already have the data, right? The missingness is artificially imputed. You can actually see, what is the original label. But in reality, with the real missingness, we don't really have the ground truth data. So we may want to manually check it, to actually see if our imputation makes sense, or if the measurement we come up with can be of high quality. So I'm gonna probably stop here, given that we're only a few minutes away, and to see if you have any questions. I want to mention that both of the appendix I've included here, I would recommend you to read into them. So they provide some how to say, the structure for how we understand the method that could be used to analyze text, for example, using neural network-based models, using BERT and GPTs. And then Appendix 2 contains how do we obtain text data using APIs. The key of using API, the reason that I didn't go into details here is that it's kind of differ based on the different APIs. We need to read into the documentation of those APIs to determine what are the parameters we used, but using the libraries and then the basic functions stay pretty much the same if we're using REST API or if we're using it from a very reliable source. So feel free to let me know if you have any questions or if you have any feedback of my workshop today. This is the first time that I offer, so I would really appreciate any feedback you have. Thank you, Carolyn. Thank you, everyone. So I will probably stop here and feel free to reach out to me personally and reach out to CSD consulting team and eScience office hours if you have more questions and play around with a Colab notebook. You can also create a personal copy of your Colab notebook to play around with it. And I'll probably see many of you in a future workshop series. Thank you all.